Good afternoon, everyone. Thank you all for coming to my talk. So today, I'm going to be talking about an open source project called Druid. And actually, just out of curiosity, how many people have actually heard of this project before? OK, wow, so quite a few. That's great. If you haven't heard of this project before, Druid it's an Apache 2 licensed column-oriented distributed database. And my name is Fangjin. I am one of the original committers behind Druid. So what we're going to talk about today is some of the history and motivation behind this project, like why create another sort of big data open source project. I want to showcase a demo of an application that was built on top of this project, just to demonstrate the value add of this project, the use cases it was really designed for. I want to talk about the problems that Druid solves, and alternative architectures you can consider for solving some of these same problems. And then finally, about half this talk, we'll do a pretty deep dive into the architecture of Druid and how data is stored and how the various components work together. So the first lines of Druid were actually started in 2011. And the project was started initially for use cases in online advertising. Specifically, what we were trying to do when we first started the project was to power an interactive analytics product for the advertising space. And the purpose of this product was to be able to look at impressions data and ads bids data and be able to slice and dice and drill into the various events that were occurring. And the main requirements of the project at that time, and some of these requirements definitely hold true today, is that we needed a very scalable backend. So if you're familiar with online advertising at all, that space can generate a tremendous volume of data. We're talking about hundreds of billions of events or even trillions of events per day. So this is like petabytes of events per day. And when we're trying to build some sort of user-facing application, you also have to consider multi-tenancy. And when I say multi-tenancy here, what I'm referring to is potentially thousands of users using the same application, hitting the same backend all at the same time. So a lot of these early requirements around scale. We also wanted the backend to power this first product to be very interactive. And what I mean by interactive is really just low latency queries. So as you're using some sort of application, you get the feeling that the application is updating or reacting to the actions that you're performing. And finally, there was this requirement of real time, which is this buzzword that's basically meaningless nowadays. But in the context of this talk, what I mean by real time is I mean very low latency data ingestion. So the ability to surface insights on events immediately after they occur. So this project, having started in 2011, was actually initially open sourced in late 2012. The first license that was chosen was GPL. And if you ever do an open source project, GPL is not a great choice for an open source license. Everyone has problems with it. The project grew slowly, and it was sort of part-time development at this advertising company until about early 2014. Around that time, there was a sufficient community, and there was this idea of wanting to put more resources behind this project. So the project was changed to Apache v2 in early 2015, and everybody loves Apache v2 because you can do anything you want with the code. And since then, the community has grown very, very rapidly. And nowadays, I think we're at easily over 150 contributors from over 100 different organizations. So Druid has grown a lot since its very early days in online advertising. It's still used heavily in that space. But this project, the system, is really designed for any type of event data. So it has also found use cases in production for network traffic data, for security data, financial data, gaming, operations, really any data that is generated by users or generated by systems. So the main use cases of Druid, how people tend to use it in the wild, is they power some sort of user-facing analytic application. And people use Druid to unify both historical and real-time events. So what is happening right now, also what is happening potentially years in the past. The type of queries that people tend to make against the system are business intelligence or OLAP queries. And in these types of queries, what you're mostly doing is you're like slicing and dicing, drilling in, looking at some filter view of data, and performing a lot of aggregations. So examples of this, this is commonly found in like behavioral analysis, like measuring distinct counts, doing retention analysis, building funnels, A/B testing, so on and so forth. A lot of people also use this system to do exploratory analytics, so trying to understand the root cause or a particular spike in their data and just drilling further and deeper into their data. So Druid, we have like a Power By page that people can openly update. Here are some of the companies that have just willingly disclosed how they're using Druid, and it's a variety of companies, both large and small, that use this system in production today. Okay, so before I jump into too many technical details, I thought it'd be useful just to showcase a demo of some of the use cases of this project and what people typically do with the data once it's loaded into Druid. And this is a live demo, so this is definitely maybe going to work. So what we have this like a public demo site, and within this site, there's a bunch of different data sources that are just public API data that we've collected. So this one, hopefully everyone can see here, the data source I'm trying to demonstrate right now is edits on Wikipedia, and this is a very common data set you see in the big data space. So with edits on Wikipedia, how the events look is there's a set of attributes related to some edit on Wikipedia, and these attributes might be the page being edited, the user doing the edit on the page, and whether or not it's a robot. There's also various metrics associated with the edit, like the number of edits that occurred, the number of characters added, or the number of characters deleted. So this is a pretty simple drag and drop UI, and if we drag time into the center here, we see how edits are trending across time. And maybe let's just pick a larger time range. So over the last 7 days, there are about 3.4 million edits on Wikipedia. Okay, so let's filter a little bit into this data. There's a lot of things you can actually edit on Wikipedia. Let's just filter on articles, because that's the thing that most people tend to care about. And here we see about 2.8 million edits that have occurred on Wikipedia, and about 1.1 billion characters added, with about 26 million characters deleted. So people tend to add a lot more characters, a lot more information on Wikipedia than they delete. And maybe let's just pick some arbitrary range of data in here between September 11th to 14th, 7 to 4 a.m. It doesn't really matter what this range is. And in this range, we have about 1.2 million edits. So let's look at some other properties of this data. Maybe we want to look at this page dimension, so this page attribute. And we drag that, and what we see is the top pages in Wikipedia being edited for this particular time range. And up here, we have Great Britain at the 2016 Summer Paralympics, typhoon season. I'm guessing this is probably a movie called Backlash, and so on and so forth. But maybe we want to do even deeper exploration. So maybe we want to know for these top pages, who are the top users editing each of these top pages. So we can do basically another operation. There's two kind of operation bars up here. There's a filter and a split. A filter is really just a where clause in SQL. So it's narrowing the field of view of your data. And split is equivalent to group by. So here we're doing a multidimensional group by on page and user. And the visualization we render is for each of the top pages being edited, who are the top users doing those edits. Maybe we want to just filter on Great Britain at the 2016 Paralympics. And let's just get rid of user here. And maybe we want to transition to another visualization like time. And here we see how that particular page is being edited. And maybe there's a particular spike that we want to look at. So we can zoom in on that spike. And we can do further and deeper exploration. There's also other attributes you can view, and there's different visualizations that get generated. For example, if you want to look at the length of comments of people doing edits on Wikipedia, this generates a bar chart, and this bar chart is fully explorable as well, as in you can filter on comment lengths between whatever particular range you want and some other particular range. So the purpose I'm trying to showcase with this demo, the purpose of Druid that's powering this UI, is the ability to arbitrarily break down and explore a data set. We're doing a lot of complex computations. We're slicing and dicing. We're looking at different views of our data. And all this is being done very, very interactively. So this UI is actually completely open source as well. It's something called Pivot. And the idea is there's different visualizations. And as you slice and dice your data, you can view your data through these different visualizations. Yeah, so this use case of doing aggregations, of filtering and grouping your data is what Druid was really designed for. So the type of data that we're dealing with is event data. So if you look at event data, it tends to be pretty similar regardless of whatever vertical you're in. There's usually a timestamp of when the event occurred. There's a set of dimensions or attributes, and these are the things that you want to filter on or you want to group on. And then there's a set of measures or metrics, and these are the things that you generally want to aggregate on or do some sort of computation over. So the types of queries that Druid is designed to solve and the types of queries that I just showcased in that demo, they're broadly categorized as like business intelligence or OLAP queries. So examples of these queries might include, how much revenue did my product generate last quarter in some particular city? Or maybe you're running a web server, you want to know how many users that visited my site last week how many of the sites visited last week also returned this week, so doing retention analysis. And in all these like OLAP queries, what you're not doing is you're not dumping the entire data set. And you're not really looking at individual events because you might have billions of events, and a single event is not that interesting. What you do instead is you filter the data, or you group it, and you aggregate it. And when you start doing these types of operations on event data, you get a much smaller result set that is easily consumable by the user. So in our demo here, as I was slicing and dicing the data, the amount of data that we're actually visualizing is not a lot. But the total data set could be gigantic. So in the types of queries that we do, your ultimate result set is typically much smaller than your input set. So Druid is not like a data processing system where your result set might be the same size as your total data set. Druid is very much like a query layer, a serving layer, something that's designed to condense the amount of data that you ultimately display or get insights from. So as you no doubt know, the whole data space is very, very complex and complicated, and there's many, many different types of solutions out there. Even for these OLAP queries, for these business intelligence queries, there are many different ways you can solve the same problem. And there's many different types of open source systems you can use to solve these problems. So for example, you might consider using a relational database, such as MySQL or Postgres. You might consider using a key value store, such as HBase or Cassandra. And now there's also general compute engines like Hadoop and Spark. And I just want to quickly go over some various ways that these different technologies approach this OLAP problem. So first, we look at the relational databases. Relational databases, they've been around since forever. Everyone has a pretty good idea of how they work. There's a pretty standard way that people typically use a relational database as a data warehouse. And what people often do is they model their event data as a star schema. And the idea behind a star schema is you have this fact table in the middle, and this contains a lot of the primary information about your event data. It also includes a lot of the measures and metrics, those numbers that you eventually want to add up. Then you have these dimension tables to the side. So you might have like a store ID in your primary fact table, and you have a store dimension table, which has additional attributes about your store. Or you have a region, and there's additional attributes about your region. And what you do is a lot of your queries involve joins between your dimension table and your central fact table. And this is, I think, really becoming outdated nowadays. I don't see many companies using this model anymore. It was very, very popular maybe about 10 years ago. And the reason why this is starting to become less and less popular is because of the performance implications. As data scales, this way of modeling data with a relational database just tends to be very, very slow. And before we actually started working on Druid, we first tried using a relational database. We were trying to use Postgres at that time to do some of these aggregations and slice and dice queries. We abandoned it when the performance just wasn't good enough. And actually, the second set of solutions we looked at before we started Druid was key value stores. And key value stores, even to this day, still remain very popular options for some of these types of queries. So HBase, Cassandra, there's various time series databases like OpenTSDB and InfluxDB that are kind of based upon this model. And what's nice about key value stores is you do get very fast write performance, and you do get very fast lookups. Because you have a key value storage model, you can get results back from your queries very, very quickly. However, when you start using key value stores for some of these analytics we've been talking about, for some of these OLAP queries, then there's limitations. So there's kind of two ways that people generally use a key value store. One of the first ways that's very popular a few years ago is through pre-computation. And the idea is try and pre-compute every single query you think your user can make, stick it in your key value store as a gigantic cache, and get results back really, really quickly. So in this example here, you might have, this is your raw data set. It has a timestamp. It has gender and age as your dimensions. And it has this revenue, which is the number you want to add up, the thing you ultimately care about. And when you pre-compute results, how results end up getting stored is your primary key might be this timestamp 1, and your revenue here is the sum of all 3 rows here. And the idea is if you query for when timestamp equals 1, then you get your result back immediately. And if you want to make a query that's for value timestamp 1 and gender equals female, then your primary key is timestamp 1, gender female, and the revenue is the sum of these 2 rows here. So if you want to support any ad hoc query, like every arbitrary combination of queries that you can make, you basically do this idea for every permutation of filters, every permutation of queries out there. And this works if your data set is very, very small and the total pre-computed query set is reasonable. Where this starts falling apart is as you start getting to more and more complex raw data sets, as you start adding more and more columns into your data, your total query space grows exponentially in size. And it's very easy that you start hitting scaling problems and storage problems with this model. But what is nice about this model is once you pre-compute all the results, you're basically just hitting a cache, doing an O1 lookup to get values back. And it's very, very fast when you do that. We tried doing this actually initially before we started using Druid. And as our raw data set just got more and more complex, it became intractable to try and store every single pre-computed value. So another way that key value stores is used to do some of these aggregations, some of these OLAP queries, is basically to do range scans. And the idea here is your primary key, instead of being a pre-computation, just becomes a hash of your timestamp and your dimensions. And your value here is the number you want to aggregate. And this model works. I think I see a lot of people still do this with Cassandra and HBase and other key value stores. But it also has performance limitations. The idea is when you do range scans, you basically have a separation between your computation and your storage. And whenever you issue a query, you have to shuffle all your data around from where it's stored into some intermediate computation buffer where the numbers are crunched and the values then returned to the user. And this shuffling of data, this scan, can be very, very slow. The reason is because it's often difficult to create intelligent indexes for this primary key in a key value store. OK, so let's look at another solution, which is a general compute engine. And that's using a system like Spark or Hadoop and combine that with a SQL and Hadoop solution. SQL and Hadoop, there's many different solutions out there. There's Impala, there's Hive, there's Spark SQL, Apache Drill, Presto, many of these. What's really nice about the SQL and Hadoop solutions is they're very flexible. They typically support full SQL. And their limitation, once again, is performance. How a lot of SQL and Hadoop engines, for example, how Presto works is you have some intermediate compute engine, again, and this might be Presto nodes, and you pull data from wherever it's stored into this intermediate compute buffer. You crunch your numbers, and then you return your results. And this like separation, once again, of your compute and your storage can have performance overhead. And I keep talking about performance, and the reason why performance is very important in my mind is as you start doing like interactive analysis of data, a few seconds, like there's a big difference between a few hundred milliseconds and like a few seconds or even a few minutes. Because when your queries start taking like 30 seconds or a minute, your application no longer feels interactive, and it's very easy to lose the user's attention. This is especially important as you're like just drilling in and exploring data, because that's a very iterative process where you might be asking some questions, getting answers, and using those answers to ask more questions. So you're just gradually narrowing down until you reach your final result. And if your queries take a few minutes to return, you've lost the user by that point. It's hard to keep your train of thought when everything takes minutes to return. So the last class of systems I want to talk about are column stores. And I think really over the last year or two, column stores have been accepted as the proper way of doing aggregations and doing some of these OLAP analytics on data. And the reason for that is column stores, they have the way that they store data is, as opposed to a row store, which is what most relational databases are, you store data individually as columns. And whatever columns actually pertain to your query actually then get used as part of that query. So if you issue a query filtered on product and price, and you want to calculate price for a certain date, you don't need to use this store column. You don't need to use this customer column. And it's just a lot more efficient for real-world queries and real-world data. Another nice thing about column stores is when you store these columns individually, you can use different types of compression algorithms for different types of columns, different types of encodings for different types of columns, and create different types of indexes for different types of columns. And these are all things that Druid does. So getting into Druid, Druid was really created out of necessity back in the day because even today, there's very few, I think, good open source column stores out there. And for us, when we were trying all these different systems, we struggled a lot with these different systems and decided to build an open source column store. So Druid, I guess its key properties, it has a custom column format that's very optimized for event data and these OLAP BI queries. It's very good for supporting a lot of concurrent reads. It supports streaming low latency data ingestion. It supports extremely fast filters. And when you kind of take these properties together, I think you have a system that's very good for powering user-facing analytic applications. OK, so let's talk about what Druid, how it actually works. So let's say we have some raw data here, and this is raw data maybe found in online advertising. So there's a time when someone looked at an ad. This is the domain where the ad was hosted, some properties about the person looking at the ad, and then whether they clicked on it or not. What Druid does with raw data as it ingests it is a process known as summarization or pre-aggregation. The idea here is if we can lose some information about time, we can gain a lot in terms of storage space. So in this example, we see that there's events that are occurring at some precise millisecond in time. But if we have like billions or trillions of these events, we don't really care about a single event that occurred at a precise millisecond in time. So what if we just lost some information about time? In this example, if we just truncate time to an hourly granularity as opposed to a millisecond granularity, then for all the rows where the set of attributes is exactly the same, then we can aggregate their metrics together. So I don't know how many rows of raw data here, but there's a lot of raw data, and it's color-coded to indicate if we just truncated our events to an hourly granularity, this is what the rolled-up data would look like. And in practice, when you start doing this with real-world data, you can easily reduce the data you have to store by 40 or 100 times from your raw data set. And this is significant cost savings in terms of storage. And you haven't lost any fidelity about the data. Like these numbers here are exactly accurate. But what you've lost is the ability to explore events at a precise millisecond in time. And this is a trade-off that you can optionally do in Druid. So the way that Druid partitions data, the way that it shards data, is actually on a time basis, and time is a very special dimension to Druid. Here we have rolled up events or summarized events across 3 separate hours, and Druid has created 3 shards, and each of these shards is called a segment in Druid. And a segment in Druid is designed to encapsulate data for a particular time interval. In this case, each segment is holding about an hour's worth of data. In our example, we only have like 5 events, but in the real world, each of these segments might hold millions of data points. So these segments, these time partition segments, they are immutable. And the reason why they are immutable is immutability confers really nice advantages. For one, we don't have to think about any contentions between reads and writes. So these segments, they're very much designed to be read-optimized data structures. And the parallelization model in Druid is that you use one thread, one JVM thread, to scan one segment at a time. So if you want to scan more data in parallel, if you want to scan more segments in parallel, you basically just add more CPUs to your cluster. So it's a nice way of being able to linearly scale the cluster. So internally, what these segments look like is data is stored in a column orientation. So example events here are just edits on Wikipedia. We might have a page being edited, and then the language of the page and other attributes. So one of the things that Druid does with string dimensions, these string columns, is it uses a method called dictionary encoding. And the idea here is for every string value, as opposed to storing the string value directly, we store some integer representation of the string. So Justin Bieber here, we can map that to an ID of 0. Kesha here, we map that to an ID of 1. And then when we actually store the page dimension internally in Druid, we store this array of 0s and 1s. So as opposed to storing variable length strings, what we end up storing is fixed length integers. And fixed length integers are much easier to compress. Similarly, language here, we just map that to an ID of 0. We store an array of 0s. The way that Druid gets very fast filters is it actually steals some ideas from search technology. So if you look at our string dimension page, again, we have 2 string values, Justin Bieber and Kesha. And let's imagine we have 6 rows of data. We can create a very fast lookup, which tells us which rows Justin Bieber occurs and which rows Kesha occurs. So Justin Bieber here occurs in rows 0, 1, and 2. Kesha occurs in rows 3, 4, and 5. And we can create this binary lookup that basically 1 indicates the value exists and 0 indicates it doesn't. So Justin Bieber here has 1 marked for the first 3 rows and 0 marked for the last 3 rows. And what's really nice about this binary index is when you do a filter on page equals Justin Bieber, Druid can do a lookup and immediately know which rows pertain to Justin Bieber. So if we had to aggregate any of these metrics together, Druid would know only to aggregate these first 3 values and skip everything else. Oops. And it's really easy to also do Boolean operations with these binary arrays. So if you ever want to issue a query that's Justin Bieber or Kesha, then you just simply do a Boolean OR of these binary arrays. And these bitmap indexes, as they're called, or inverted indexes, if you're familiar with the search world, these arrays of 0s and 1s are very easy to compress, and they're not very expensive to store as well. Cool. Druid also supports a plugin architecture, and most people use the plugin architecture to create their own types of computations or calculations. So there's various approximate algorithms like hyperlog or approximate histograms, or you can even do approximate funnel analysis in Druid. And I think approximate algorithms are very, very powerful for very fast queries, and I think they're underutilized in the big data space. So I just want to talk a little bit about how approximate algorithms work in Druid and why they're awesome. So when Druid ingests data, it does this process called summarization, which can really reduce the volume of data you have to store. But summarization requires on having the same dimension values across different events. If you have a very high cardinality dimension with a lot of unique values, such as a user ID, it basically prevents rollup or summarization from happening because all these values are unique. You can't roll up your data anymore. The idea behind an approximate algorithm, like how hyperlog or many of these like count distinct approximate algorithms work, is instead of storing every single unique user ID, you store information about how many unique users you've seen over some span of time in this probabilistic data structure. And it's usually called a sketch data structure. But the idea of how it works in Druid is you can, instead of storing every single unique ID, you store users as this metric instead. And what it enables is enables you to roll up the data once again. And this is really nice in that rollup confers all the storage advantages I talked about before. And when you store less data, your queries often go much faster as well. So for a 98% accurate result, what you're getting is potentially 100x less storage space and 100x better performance. So a lot of people still say accuracy is very, very important in the big data world, but I always feel that 98% or 99% accuracy is probably good enough for all the advantages that you get from it. OK, going a little bit more into the architecture of Druid and how everything works. So Druid has two ways of loading data. There's a batch ingestion method, and there's a streaming ingestion method. The way that the batch ingestion method works is you have static data in HDFS or some other file system, and you can run a MapReduce job with Hadoop or Spark and generate these Druid segments. And these Druid segments then get loaded across a set of processes or nodes called historical nodes. These guys are very simple. They know how to load segments and respond to queries on segments, and that's all they do. In front of the historicals, you have a set of broker nodes. And these guys do query scatter gather functionality. So queries get sent to a broker. They know which segments live on which historicals, and they forward those queries down. And these guys crunch answers in parallel, and these guys merge results before they're returned to the caller. Druid also supports real-time ingestion or streaming ingestion. And the high level behind how streaming ingestion works in Druid is you have two different data structures. You have a write-optimized data structure and a read-optimized data structure. So if you recall what I said before, segments are immutable. But like Druid has to support writes because you have to get data in somehow, right? The way that the write-optimized data structure works is it's basically just a giant in-memory buffer. And events are written to memory as fast as possible. And because this guy is not very read-optimized, you periodically convert the data in this in-memory buffer into the Druid segment format. So you have this forever going process of events being written to memory and converted to the Druid segment format. And while all this is happening, Druid can answer queries on both these pieces. And when you put it all together, how Druid works as a system is you stream data into these real-time nodes or these real-time workers who then periodically create segments and hand off to these historical nodes. The idea is historicals are read-only, brokers are read-only, and real-time nodes are read-write. And because read-write is a much more complex operation, these guys only ever hold a small window of data. So they might only ever hold about an hour's worth of data. And these guys can hold then years' worth of data. And the broker combines both the real-time view and the historical view, and you have a unified view of your system. You put it all together. When you do both batch processing and stream processing, you have your classic Lambda architecture. So getting data out of Druid, the native query library is JSON over HTTP, but there's also community-contributed libraries for SQL, R, Python, Ruby, Perl, and pretty much every language you can imagine. There's multiple open source UIs. There's Pivot, which I just demoed. There's Grafana, if you're from the operations world. And then Airbnb actually created a dashboard called Caravelle that you can use as well. OK, so last two sections here. One is just on some production numbers. This is from a very large cluster, and some of these numbers are public, so I just pulled these numbers from there. Largest cluster I'm aware of is doing about 3 million events per second sustained, or about 200 billion events per day. And this comes out to roughly about 10 to 100,000 events per second per core. Largest known cluster is serving, I think, close to 100 petabytes of raw data at this point, probably closer to 100 trillion raw events. And when you take these raw events and you summarize them and you compress them, it turns out to be about 500 terabytes or so of segments. And at this massive scale, I think Druid is a very cost-effective solution. In terms of query latency, in this cluster, it's about 500 millisecond average query latency. 90% of the query is less than a second, 95 less than 2 seconds, 99 less than 10 seconds. And the cluster gets a few hundred queries per second. This slide is actually a little bit out of date because I'm now aware of a couple of different production clusters that are at now a few thousand queries per second. OK, so very last section here is how Druid kind of fits in this whole wacky data space as an open source solution. This is an architecture I like a lot. This is an architecture which I think is flexible to handle a lot of different types of use cases with event data. And in this architecture, you have events that get fed into a message bus. Nowadays, I think Apache Kafka is by far the most popular open source message bus here. And then it's fed to data processing systems, so systems to clean or transform the data. And here, in the stream processing world, there's many different solutions. There's Storm, Spark Streaming, Flink, Kafka Streams, and so on and so forth. In the batch processing world, there's Spark and there's Hadoop, and I think those are the two primary ones. And after your data is transformed or cleaned, then it can go into a system like Druid, which basically supports Lambda architectures out of the box. And over time, I think this batch processing piece will probably go away, and you can have this really nice end-to-end streaming analytics stack. But yeah, I mean, Druid is very much designed to be complementary to all the popular open source big data solutions out there. And it works out of the box with Kafka. It can actually support exactly one's consumption from Kafka. It works with RabbitMQ, Spark, Hadoop, Flink, Spark Streaming, Storm, so on and so forth. And we're spending a lot of time right now making Druid work really well with the SQL and Hadoop solutions. So we imagine a world where people can query Druid from Hive or Impala or Spark SQL or Drill or Presto, or really anything else they have in-house. Cool. So with that, I'd like to conclude my talk with hopefully some of the takeaways that you got from here. I think Druid is pretty good for analytic applications. I think it's pretty good for OLAP queries. So if you want to filter or slice and dice and group data, I think it's a pretty good choice. I think it's pretty good at streaming ingestion. So if you have a stream of event data that you want to load into a system, it has really nice properties around streams. And it also works very well with a lot of existing data infrastructure systems. So whatever you have in-house, Druid should work with it. And if you ever want to try Druid out, we have a link up there. That's our quick start, and you can play with the UI I demoed and play with the system as well. Cool. Thank you, everyone. I think we only have a few minutes left, but I guess I can take a few questions. Yes, I think your hand went up first. So I heard about half of that, and I heard what is the data storage engine for Druid, and I think something hash table. What was it? OK, B-tree or hash table. OK. So the data storage engine of Druid is completely custom. It's a custom column format. So there's really no B-tree in there. Every data is stored as individual columns, and the indexes that get created for those columns are inverted indexes, or those bitmap indexes I showed earlier. So Druid, I guess, is a little bit different than a traditional column store in that it has a lot of ideas from search kind of baked in as well. Yeah, but yes?
You're talking about rolling up individual user IDs into like sort of clusters, like user ID profiles.
Yeah.
Was that actually being done with Wikipedia people, or does it look there like you have individual user IDs for the Wikipedia?
Right. So the question was around how user IDs get rolled up and whether or not it was being done for that Wikipedia example. So for this example here, I think there's a column called unique users. And let me just pick a larger time range here. So this unique users metric is being done approximately. And the idea, yeah, this is rolled up data. So all the data I'm being demonstrated here has roll up kind of baked in. All the data here, I believe, is being rolled up to a minutely basis. So with so this dimension, the number of unique users here, this is no rollup. This is actually storing the user ID dimension. We've actually approximated it just for faster calculations as a metric as well. Yeah, so it's actually being stored twice in this example. I think this was first.
So if I use something like Hive and a row-oriented storage, I can still aggregate. It might not be as performant, but I have the row-level access and the slower aggregation.
Right.
Get back to the row-level here, and if not, what solution do you see for supporting both access patterns in the same ecosystem?
Right. So the question was around basically integrating Hive with Druid and how like different query operations would function across the two systems. Is that a good summarization? Right. So there is actually quite a bit of work that's being done out there right now around Hive Druid integration. And the idea of that work is Druid primarily gets used as an OLAP index for Hive. So for a lot of the aggregation queries, a lot of the filtering, slicing, dicing OLAP queries, they get pushed down into Druid by Hive. But for queries that Druid can't support right now, some of the row-level queries that Hive supports, then the idea is it would use Druid select query and just pull data from Druid into Hive where the calculation is done. Yes.
Does the event schema have to be fixed in advance before you start ingesting, or how do you deal with schema?
Right. So the question is around, does the event schema need to be fixed beforehand, and how does Druid deal with schema evolution? So the short answer is it does not need to be fixed. There's a lot of flexibility in Druid to be able to explore. It's not fully like unstructured data. What you have to provide Druid is a set of metrics, so the things you want to aggregate, and also what the timestamp column is. And then Druid can figure out what all the other dimensions are as part of an event. The reason why metrics need to be provided is so that Druid can understand how to roll up data if it has to roll up data. The idea with evolving schemas is that every segment or every partition in Druid is very self-contained. So every partition has its own schema. So even for the same table, partitions don't need to have the same schema. And how Druid treats operations across two separate partitions with different schemas is basically, let's say one partition has a column, the other partition doesn't, and you issue a query for that column across both those partitions, then Druid just treats all the values in the second partition as null. So like a very common use case is to have an evolving schema with time. Yes?
Does the same apply when you say there's a different schema for each segment? Does the same apply for like the dictionaries?
Yes. So all the dictionaries that get built, the question was, does the same idea apply for dictionaries within a segment or within a table? So dictionaries are built on a per segment basis. So every segment has its own local dictionary. So one dictionary from one segment to another, they're completely distinct, and Druid has logic to merge the dictionaries together, basically. Cool. Any other questions? Yes?
Is your dictionary based on prefix trees?
No, it's actually very, very simple, the dictionary that's in Druid. It's basically every unique string value it finds, it maps it to a dictionary ID. We haven't tried that yet. Right now, there's no like kind of global dictionary in Druid. It's all done on a each dictionary is on a per partition basis.
Can you talk a little bit about joins in Druid?
Okay, right. So the question was around joins in Druid. Right now, Druid supports like star schema joins. So if you have a large table and a small table, Druid is able to do that join pretty efficiently. If you're doing a join of a billion row table with another billion row table, Druid currently doesn't support that, and that's part of the work we're doing with integrating Druid SQL and Hadoop engines, because we think that over time, we're just going to have like Presto or Spark SQL talk to Druid, and it'll be Spark SQL or Presto that does the join. The star schema join, the large table, small table join is easy to do. The large table join is a lot more complex and a lot more resource intensive, and that's part of the reason why we haven't done it yet. But within the next quarter or so, we anticipate it'll probably get done.
We need to get.
Oh, sorry, I'm getting kicked off. I'm going to clear out the stage, but I'm happy to take more questions in a second. Thank you.